Hello everyone, I'm Guillaume Florin, and today I'm going to present a study carried out at Macquarie University about first metal grains formation in the early solar system. So before planetary formation, 4.5 billion years ago, the solar system was in the form of an accretionary disk mainly composed of gas with a young and hot sun at its center. With time, that disk had cooled and collapsed, allowing the gas to condense in fine dust particles of silicates, metal, and sulfides that are going to be reprocessed during heating events. This is the next generation of these particles that we are studying here in order to understand the first step of solar system formation. So to do that, we are using meteorites, and within the numerous meteorites group, one of the best candidates to study metal phase formation are ordinary chondrites. And this is because they are composed of pristine silicates, metal and sulfide grains, which mean that they haven't experienced planetary differentiation, meaning that the metal and the silicates haven't been segregated into a silicate mantle and a metallic core to form a planet. Therefore, this kind of object seems to be samples of early formed undifferentiated planetesimal. So in that study, we are interested in metal phase formation, and many processes can be highlighted for that processes and for metal evolution. For example, metal can be formed by direct condensation or recondensation. Metal can be formed by silicate reduction and iron nickel extraction, or metal can be formed by the melting of metallic precursor during heating events within the protoplanetary disk. However, in the case of ordinary chondrite, condensation and silicate reduction can not explain the elemental composition of the metal. The formation of metal phase in ordinary chondrite is therefore subject to debate, and two main hypotheses exist. The first one suggests that highly siderophile elements rich grain have been incorporated within the metal during metal formation. Working in favor of incorporation, a study of Florin and collaborators in 2009 have shown an inverse correlation between highly siderophile element content and the grain size, which cannot be explained by the melting of a metal precursor with 0 to 25% of sulfur, as it's highlighted in the diagram on the right. They also found a lack of correlation between highly and moderately siderophile elements within metal grain, arguing in favor of the incomplete homogenization of refractory phase within metal grain. In addition, they demonstrate that compared to large metal grain, small ones have a high palladium on iron ratio, pointing out condensation at high temperature. However, more recently, another study contradicts this model, and on the basis of in situ analysis of highly siderophile elements, they suggest that metal signature is a result of heating event followed by melting crystallization. However, that model proposed a value of 2% of carbon in the metal to reproduce the variations of composition, far from the total metal bulk reported in iron, which lie from 0.7 to 1.5%. Also, their model doesn't include sulfur, whereas ordinary chondrite contain up to 4% of sulfides. So there is currently no consensus of metal formation in ordinary chondrite, and understanding the formation of that particular phase will help to constrain early stage of protoplanetary disk evolution. And the goal of that study is to constrain the formation of metal in H-ordinary chondrite before accretion by comparing highly siderophile element and moderately siderophile element. So to do that, we did some in situ analysis using LRI-CPMS technique, and we analyzed highly siderophile element and moderately siderophile element using iron, sulfur, and nickel as external standard, as internal standard, and two external standard, PGA and Philomena, which is an iron meteorite. So we have studied the repartition of siderophile element in the metal grain to explore metal fusion and crystallization. Indeed, experimental studies show that elemental fractionation vary between elements and between liquid and solid. For example, if we consider a pure iron-nickel phase, the iridium is a compatible element, whereas germanium is incompatible. But if we increase the percentage of sulfur in the metal phase, the germanium can become incompatible. And this is the same for example, carbon. And the difference of compatibility between these two elements during metal melting and crystallization is always similar, whatever the proportion of sulfur and carbon you are adding in the metal. This means that the first or the last liquid, depending if we are studying melting or crystallization, will always be enriched in germanium compared to iridium, meaning that the germanium and iridium ratio is a good tracer for these processes. So here are our results, and what we can see at first glance is that there is a large variation between each metallic grain, and this suggests that there are many different compositions within a same sample. But if we look at the germanium, the germanium is very well constrained and there is not a lot of variation, whereas for iridium, there is a lot of variation. And because we are studying very pristine object, these variation reflect nebular processes. If we now report our measurement against the germanium on iridium ratio, we can highlight an inverse correlation between highly siderophile elements and moderately siderophile elements and the germanium on iridium ratio. The striking point here is, as previously said, the large variation of composition from one grain to another. Regarding this correlation, we have developed a batch melting model to try to explain these two correlations. So you have here an example of our model. We report the osmium, again, the germanium on iridium ratio. You have in red the liquid composition, in green, in red the solid composition, in green the liquid composition, and the yellow star is the starting composition. The area in gray is the range of composition that can be made by mixing a solid and a liquid. The blue points on the diagram are our results. And what we can see is that with a batch melting model, is it possible to fit our data? And to do that, we use a metal composition with 1.5% of carbon and from 0 to 12% of sulfur. The multiple sulfur content suggests that there is that the sulfur content of the metal is locally defined during probably a heating event. Now, this composition now these correlations, are working for plenty of different elements, but something is not working, and that it's impossible to fit the point, our data that are above the liquid curve here, highlighted by the yellow arrow. And this point that doesn't follow the model are only for for refractory elements and for the liquid. So we suggest that this high value reflect the incorporation of highly siderophile rich refractory particles within the liquid during metal melting. Yeah. So to sum up, the metal composition in ordinary chondrite can be explained by precursor melting that had contained 1% of carbon and from 0 to 12% of sulfur. This is in line with carbon content in unequilibrated ordinary chondrite. Also, the liquid metal and solid metal has been mixed during that heating events, and the liquid have probably incorporated high content of highly siderophile element particles that were refractory. So thank you very much for your attention.